Hello to everyone. Today we'll be discussing the determination of the Raman, determination of the structure of the molecule with the help of the Raman and the infrared spectroscopy. In last class, I have discussed about the utilizing the depolarization property from the molecule. With the help of the Raman spectroscopy, we can find out the structure of the molecules. That is especially for the symmetrical top molecules, spherically symmetric molecules. That is one kind of the category of the symmetrical top molecules. Today, with the help of the, as I said, that it is always be easier to determine the structure of the molecules with the help of the infrared spectroscopy and the Raman spectroscopy. And there is a very strong the principle of the mutual exclusion. Once you have a center of the symmetry, then only one mode, either the Raman spectra you will get or the infrared spectroscopy peak observation you will be getting. So will be in the general case some of the examples in combination of this Raman spectroscopy and the infrared spectroscopy. We will try to find out the structure of the molecules, and we have already done that for the linear diatomic molecules CO2 and the N2O, the water molecule. Let's see the similar example, and we are taking the limited discussions based on the some of the molecules. For example, the CO2, N2O, SO2, and these. So, and we will extend this. We will extend the these methods to determine for the generalized case of this AB of 3, AB3 type of the molecules, then we'll see that whether it having the planar symmetry or the pyramidal symmetry. Dealing the first triatomic molecule AB2 type, once this AB2 type of the molecules. Now, question is that whether this molecule is the linear molecule or the non-linear molecule, whether it is a symmetrical or the asymmetrical one, whether it is a symmetrical one, this B of A of B, or the asymmetrical type of this A or B of B of A, or this A of B type of the molecule. So in the case of the carbon dioxide and the nitrogen oxide, both molecules give rise to some infrared bands with the PR counters. They must be therefore the linear, because they are giving the IR, so they must be the linear. The mutual exclusion principle rule that CO2 has a center of symmetry. CO2 having the center of symmetry. CO2 means this is a O of CO, center of symmetry, and N2O, this is N of O. And only this case, only N2O having the bands common both in the infrared and the Raman. It means that this is not a center of symmetric molecule. So with the help of this method, now it is completely we can find out the structure of such molecules. Now another example of SO2. Now the observed data for the SO2, infrared and Raman bands for the SO2. If this is a wave number and this is the IR, this is Raman. So at 519 we are getting this parallel type band, and this is a polarized, and we'll be getting that 1151 second type of parallel type of band, again it is a polarized, and this 1361 perpendicular type band and depolarized. So the Raman absorption and Raman IR spectra are collected in this table for the SO2 molecule. So immediately we could say, because we are getting the PR, these bands in the Raman and the IR, it means that it is not a linear molecule, not a center of symmetric molecule, since all three fundamental are Raman and infrared active. In an infrared, all three bands show very complicated rotational fine structure, and it is evident that the molecule is a non-linear. So the band shows the simple PR structure of, say, carbon dioxide. The molecule has that bent shape. It means that this S, if you remember for the carbon dioxide, what the band is, we have this band structure. Because I'm getting the both the side, all the three bands are appearing in my Raman and the IR, it means that it is not a symmetric molecule. And some band structure, that is why it is giving the both the IR and the Raman spectroscopy. Now this is the AB2 type of the molecules. Now we are generalizing that another method, generalizing that the molecule of AB3 type molecule, AB3 type molecule, then the total fundamental frequencies we can calculate 3n minus of 6, 3n minus of 6, then this number of the molecule 4, then you have a 6 fundamental bands. But we'll see that we'll be getting only 4 bands. The reason is that you have two states, two fundamental frequencies have the double slit degenerate. That is why then you are only getting the 4 one. So the symmetric planar and the symmetric pyramidal shapes. So we'll be expecting that the two kind of the symmetrical molecules, either planar geometry or the pyramidal geometry. The planar geometry means all the molecules are in the same plane. On the other hand, pyramidal, you have a kind of the pyramid structure of the molecules. Okay. So we'll be making a diagram. So in this case, the doubly degenerate two state, the symmetrical stretching one, we have the doubly degenerate, and one is the angle one. So both are these, either I am taking that the pyramidal or the planar geometry, both are the symmetrical ones. So both the molecule shapes are in fact a symmetric top with the main axis passing through the A. So main axis passing through A perpendicular to the B3 plane. It is with respect to the axis that the vibration can be described as parallel or perpendicular. With that particular plane, we can define my vibration perpendicular or the parallel to it. In particular, for a symmetric planar and a symmetrical pyramidal shape, one stretching mode and one angle deformation mode are each doubly degenerate. So this is a symmetric planar. Activity R Raman. This is showing that the Raman, and this I infrared. Then this column showing that the vibration, and this column is pyramidal, and this is the activity Raman and IR. We'll see that all the 4 variations. Now planar geometry, suppose I have this A, B, B and B. So symmetrically moving, it is outside, it's all the molecule of this planar geometry B is moving outside. Then in this case, you have R active and polarized. Then I is inactive, because you have a center of symmetric molecule. And the vibration is your V1 symmetric stretch. So here you have A, B, B and B, pyramidal structure. So then you have all the vibrations are symmetric one. R is active, that is a polarized strong, and I active parallel. So another type vibration, V2 out of the plane symmetric deformation. Out of the plane but symmetric deformation. Symmetric deformation. So in this case, you have this A and this B and B. So this is moving upwards, this is moving upwards, this is moving upwards, and this A is moving downwards. So R is inactive, and I is active parallel. And here you have this A, B, B and B. This is moving up, this is moving up, this is moving up, and this is moving down. Pyramidal geometry. So here you have this R is active polarized and I active parallel. So the third fundamental vibrations. So this V3 asymmetric stressing. Asymmetric stressing this A, you have this B and this B. So this B is moving downwards. These are also moving downwards. This B is moving down, this is moving B down outside. This B is not going up, it is downwards. So here you have this R active depolarized and weak and I active perpendicular. So because the principal axis which is passing through this A molecule and which is perpendicular to this B3, this V3. Now you have this axis, this B is somewhere here. If in this case you have a planar geometry, but here you have a non-pyramidal one. So this is my axis. So in this case you have this A, B, B and B. So this is going up, this is going out, and this is going out. And this R you have active, depolarized, weak, and I active perpendicular. And the last fundamental frequency, this new V or 4, asymmetric deformation. Asymmetric deformation. It was a symmetric deformation, it was a asymmetric deformation. So you have this A, you have this B, and this is B, and this is B. You have this A, B, and this B. So this B is moving this way, and B is moving this way, and this B is moving up. Here, this B is moving this side, this B is moving this side, and this B is moving this side. So this bond is not kind of these bond angles are changing. So in this case you have this R active, depolarized and weak, and this I is active and perpendicular. Here is you have this R active, depolarized, weak, and I is active and perpendicular. So the symmetric molecules of the vibration are parallel and Raman polarized, while the asymmetric are perpendicular or the polarized. The symmetric mode of vibration are parallel and the Raman polarized are the, while the asymmetric are perpendicular and the polarized. So all the vibration of the pyramidal molecule change both the dipole moment and the polarizability. Hence all are having the active. So you have the R active, I active, R, I, R. Everywhere these are the active. However, you have in this case the symmetric stress, R is active, I is inactive. Symmetrical deformation, R is inactive and this your IR is active. However, once you have an asymmetric stretching and asymmetric deformation, you have both the active I and both the I and the R are the active in this case. So the symmetric stretching mode V1 of the planar molecule, however, leaves the dipole moment unchanged, remain zero throughout, and so the infrared inactive, while the symmetric bending mode are not change the polarizability, and the V2 is Raman inactive for planar AB. So for this one, it is a Raman inactive. So if we'll see that the overall these are the experimental findings, then we are predicting that the structure of the molecule AB3 type of the molecule. So if we will conclude that planar AB3 type molecule, number one, vibration Raman active only V1, number two, infrared active only, that is the V2 mode, and number three, vibrations both Raman and IR active, that is the V3 and V4 mode. So in a V3 and a V4 mode, you have a doubly degenerate. And a pyramidal AB3, all four vibrations, both Raman and IR active modes. You have seen that from that table, this AB3 having this pyramidal shape, having all the vibrations, that is the Raman active. So once you have a non-symmetric symmetric AB3 type, it means that possibly more than 4 fundamental frequencies will be available in that case, because you have an asymmetric case of this AB3. It means that there won't be any kind of a degeneracy. So the symmetry is always reflecting in terms of their degeneracy of the energy states. So now for the just AB3 type molecule, this is a plain geometry, then only this first the vibration Raman active only V1 frequency, that is the symmetric stretching of the bond, and the infrared active only once the symmetric deformation of the angles. However, for the asymmetric stretching and asymmetric bending, angle deformation, you have both the IR and the Raman actives. For the pyramidal, you have seen that all the Raman and the IR active for all the four fundamental vibrations, and the non-symmetric molecules AB3, once you have a non-symmetric molecules, then we may have more than 4 fundamental frequencies because you have an asymmetry of the molecules. So in this fashion, we can find out with the help of this Raman spectroscopy and the IR spectroscopy, we can find out the structure of the molecules, and utilizing that the exclusion rule. So now we are closing this unit, the Raman spectroscopy, at this point, and now I will start Monday onwards the electronic spectra. So for this chapter, I would suggest you please go through the Benwell's book that I've already provided you all. for a study material, and at least this unit you go through from that particular book, so it will be very helpful for you. So now the next class I'll be discussing that the electronic spectra of the molecules. Thank you.